This video deals with two very important counting techniques. The concepts are permutations and combinations, which are related but in some ways quite different. These tools are not only useful for counting, but they also provide very important underpinnings for the study of probability, which is going to be coming up shortly in this class. To introduce the idea of permutations, we'll return to consideration of this fellow Ed and his choices for shirts. Remember, he had a white shirt, a blue shirt, and a yellow shirt. Let's suppose he's going to wear a different one on each of the days, Monday, Tuesday, and Wednesday. So he's got the 3 shirts to match up with the 3 days. How many ways can he match up the 3 shirts with those 3 days he's going to wear one shirt each day? We have a picture here that illustrates the choices. He could wear the white one on Monday, the blue one Tuesday, the yellow one Wednesday, or white Monday, yellow Tuesday, blue Wednesday, blue, white, yellow, blue, yellow, white, yellow, blue, white, yellow, white, blue. I don't think you have to look at this picture very long to convince yourself that that's all the possibilities if Ed is going to wear a different shirt on each of those 3 days. The reason that there were 6 choices is because, in effect, he's arranging his 3 shirts in a particular order. One for Monday, one for Tuesday, and one for Wednesday. The number of ways of making that arrangement is he has 3 choices for which clean shirt to wear the first day, and then he'll have 2 clean shirts to choose from the second day, and only 1 remaining for day 3. So basically, 3 times 2 times 1 is simply an application of the multiplication principle. In that calculation, we were multiplying the integers from 3 down to 1. That's done so often that there's a special term used to describe that. The term is called factorial. If n is a positive integer, then n factorial means the product of all the integers from n down to 1. For example, 5 factorial is 5 times 4 times 3 times 2 times 1, which is 120. Lots of calculators have a button on the calculator that evaluates factorials for you, so you might want to explore your calculator and see if you have such a button on your calculator. So now let's formally come to the term permutations. It has a specific meaning. A permutation of a set of objects simply means an ordering of the objects in some specified order. And the number of different permutations of n different objects is given by n factorial. The example that we just saw with Ed's shirts, he had 3 shirts, and we saw that the number of ways of ordering those 3 shirts to match up with 3 days of the week was 3 factorial. If you were ordering 5 things, the number of ordered arrangements would be 5 factorial. The number of permutations of n distinct objects is n factorial, no matter what integer n happens to be. A baseball team has 9 players. How many possible different batting orders are there? Second version of the question, how many batting orders are possible if the pitcher is going to bat last, which is the way it's commonly done. The first question, how many different possible batting orders are there? No reference to the pitcher. It's simply a question of how many ways can you take the 9 players and order them in some particular fashion, since a batting order is nothing more than an ordered arrangement of the 9 players, specifying who bats first, who bats second, and so forth. There are 9 players. The number of ways to write down a batting order would simply be counting the permutations of the 9 players, counting the number of arrangements, the number of ways to list them in order. That would be 9 factorial, since it's 9 choices for who bats first, and then 8 choices for who bats second, and so forth. 362,880. However, if you're going to specify that the pitcher should bat last, then the only arranging to be done is with the first 8 batters, the 8 people who bat before the pitcher, could be arranged in 8 factorial ways, since you're just simply counting the number of permutations for those 8. 8 times 7 times 6 down to 1 is 40,320 possible arrangements if the pitcher is going to be batting last. Some special notation that's involved with permutations. Given a collection of n objects, the number of different ways in which r of them can be lined up in a row is written as p of nr. So p stands for permutations, of course. N is the number of objects you have in the collection, and r is how many of them you're going to be lining up in a row. And the number of ways of doing that is the product of the numbers from n down to n minus r plus 1. This kind of ordered arrangement of r objects chosen from a set of n objects is called a permutation of r objects chosen from the n. So for example, if you're choosing from 8 and 3 is how many you're going to choose, the question then is how many different ways from a batch of 8 objects can you choose 3 and line them up in a row? This expression reduces to a product of 3 numbers from, in this case, n is 8 down to n minus r plus 1, which in this case would be 8 minus 3 is 5 plus 1 is 6. So you'd be looking at the product of numbers from 8 down to 6. And the reason that it's this product is because if you're lining up 3 objects in a row from a batch of 8 objects, you have 8 choices for your first object, and then once that one is chosen, you have 7 remaining possibilities for your second object, and then 6 choices for your third object. So really this is nothing but the multiplication principle that causes this to be true. But bottom line here is that the number of different permutations of 8 objects choosing 3 of them is 336. If you have 5 clean shirts and you're going to pick one to wear on Saturday and another different one to wear on Sunday, how many possible ways can you make your choice? Well, you're choosing from a batch of 5 shirts. 2 is how many you're choosing. P of 5, 2 is just 5 times 4. 5 choices for which one you wear Saturday times 4 remaining choices for which one you wear Sunday. 20 possibilities for the number of ways to make those 2 choices. If you have 5 clean shirts and are going to pack 2 of them to go on a weekend trip, how many possibilities are there for the 2 that you select? Be careful here, because if you want to say 5 times 4, you're not really looking at the question that's being asked. This is a little different kind of question, so we need to think carefully. There are 10 possibilities for which 2 shirts you pick, and they're shown right here. You can decide to pack your white and blue shirt, or your white and yellow shirt, or your white and red. The 10 possibilities are shown. Remember, this is what we had to choose from: white, blue, yellow, red, and gray. And you should be able to look at the 10 possibilities that are shown and convince yourself that indeed, if you're going to be picking 2 shirts to pack in your suitcase from that batch of 5 shirts, then these 10 possibilities are all that there are. 5 times 4 would give you 20. We don't have 20 possibilities, we have 10. So what are we doing different here from what we were doing when we were talking about permutations? This is our introduction to combinations. A set of R objects chosen from a set of N objects is called a combination of R objects chosen from N objects. And the number of different combinations is given by the formula shown right here. If you're choosing from N objects and R is how many you're choosing, then the number of ways of choosing that set of objects is N factorial divided by R factorial and also divided by n minus r factorial. So combinations, when you're counting combinations, you're in effect counting the number of different unordered sets of R objects that can be chosen from a set of N objects. So the fundamental difference in combinations and permutations is that when you're talking permutations, you're talking about ordered arrangements from a set. And when you're talking combinations, you're talking about just sets of objects which don't have any order associated with them. In the case of the 5 shirts, where we were choosing 2 of them for a weekend trip, we counted the 10 ways to do it, and the combinations formula would give us 10 because 5 here is the number of objects, 2 is how many we're choosing. You plug those numbers into the combinations formula, and that gives you 5 factorial, n factorial is 5 factorial, 2 factorial, and 3 factorial are the 2 terms in the denominator, and the arithmetic there produces 10. So the combinations formula does give us an answer that's consistent with the 10 ways that we counted before looking at the formula. Jerry has 7 CDs that Michelle would like to borrow for a party. He's agreed to let her take 4 of them. And how many different ways could Michelle make her choice? It's simply a question of how many ways can she choose 4 CDs from among the 7 that are available. That's a combination situation. How many ways can you choose 4 objects from 7? The number of ways of doing that would be 7 factorial divided by 4 factorial and divided by 3 factorial. And the arithmetic there reduces to 35. This is different from what permutations of 7 objects choosing 4 would be. Permutations of 7 things choosing 4 would be 7 times 6 times 5 times 4. That would be the number of ordered arrangements. We're not taking these compact disks and counting how many ways to arrange 4 of them into some specific order. Order doesn't play any role in this question at all. It's simply a question of how many different ways you can choose a batch of 4 CDs from the 7 that are available. Take a look at the arithmetic that's involved in evaluating this kind of expression with factorials. If you do cancellation, it actually evaluates very quickly. You start multiplying out the numerator, 7 times 6 times 5, and then everything else in that numerator would be canceled with the 4 factorial, and it would leave you a 3 times 2 from the 3 factorial, which you would cancel with the 6 upstairs, and that would leave you just 7 times 5, or 35. So write out enough of these factorial expressions to see how the cancellation works, just to make sure that you can quickly manually do calculations like the 35 ways that's shown here from this expression involving the factorials. This is a summary of what I just said. With the 7 factorial, you start multiplying that out. 7 times 6 times 5. Everything else in that product in the numerator would cancel with the 4 factorial. You're left with a 3 factorial in the denominator. 3 times 2 is 6. Cancel the denominator with the 6. 7 times 5 is all that you have left in the numerator. That gives you the 35. A class consists of 14 boys and 17 girls. 4 students from the class are to be selected to go on a trip. How many ways can you make that selection of the students? And second version of the question, how many ways can you select the students to go on the trip if you're going to split the group of 4 into 2 boys and 2 girls? For the first version of the question, how many different possibilities are there for the 4 students selected to make the trip? In this instance, we're selecting from how many people? We have 14 boys and 17 girls, so that's 31 students altogether, and our only task is to select which 4 of them go on the trip. So it purely and simply is a matter of selecting 4 students from the total group of 31 students. That's a combinations type question. We're simply counting the number of ways to select a set of 4 from a set of 31. Plug those numbers into the combinations formula, and we count 31,465 possibilities for the 4 students selected to go on the trip. Now, in the second version of the question, where we want to choose 2 boys and 2 girls, we have to count a bit differently. The easiest way to think about this is to simply split it up into 2 different problems. One of the things we have to do is to pick which 2 boys are selected to go on the trip from among the 14 boys, and then we have to pick the 2 girls from the 17 available girls. So think of the whole process as a matter of doing each of those 2 things. We have to pick 2 of the 14 boys, and we can use the combinations formula to count the number of ways of doing that. Then we have to come along and pick 2 of the 17 girls. We can use the combinations formula again as a way of counting the number of ways of picking the girls. But finally, I have to then multiply those 2 numbers. Why do I multiply? Well, it's just the multiplication principle all over again, isn't it? If I can pick the boys in this many ways, and if I can pick the girls in this many ways, then the number of ways of picking the 2 boys and the 2 girls is the product of those 2 numbers. So we do combinations of 14 boys choosing 2 of them, and the combination formula will give us 91 ways to pick the 2 boys. The combinations formula will also give us 136 ways of picking the 2 girls. 91 ways to choose the boys times 136 ways to choose the girls gives us 12,376 possibilities for which 4 students go on the trip, provided we've agreed to select 2 boys and 2 girls. For many variations of poker, you deal 5 cards to each player from an ordinary 52-card deck. Let's consider how many different poker hands there are. How many different ways could you be dealt 5 cards from a 52-card deck? And then secondly, how many of those hands would give you a full house? A full house is a hand that contains 3 cards of one rank and 2 cards of some other rank. For example, you might have 3 aces and 2 sevens. So we have 2 different questions here. We want to count the number of poker hands, and we want to count how many there are that contain a full house. To count the number of poker hands, that's a straightforward combinations calculation because we have 52 cards in the deck, and the poker hand consists of 5 of those 52 cards. The combinations formula gives us the way of counting that, and you come out with around 2.5 million different possible poker hands. Now, the number of hands that give you a full house is obviously going to be much, much, much smaller than that, a much smaller number. Let's see how you would count that. There are 13 different rank cards in the deck: 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King, and Ace. So a full house consists of 3 cards of one rank and 2 cards from some other rank. So let's think of first counting the possibilities for the ranks of the cards, the rank from which the 3 will come and the rank from which the 2 will come. If you think about where the 3 cards come from first, there will be 3 alike coming from one of the 13 ranks, and then 2 alike coming from one of the other 12 choices for remaining rank. So that gives us 13 possibilities for which rank it is that the 3 cards alike come from, times 12 possibilities for which possible rank it would be that the 2 cards alike would come from. And then let's think about the cards within that rank. Suppose, for example, we know we're going to have 3 aces. How many different ways could you have 3 aces from the 4 aces in the deck? Well, it's just a matter of how many different ways you could pick 3 of the 4 aces. And if your 2 cards alike were going to be the sevens, then you have to consider how many different ways you could pick 2 of the 4 sevens in the deck. So to summarize here, I'm looking at the multiplication principle. This is a moderately complicated example, isn't it? But I'm using just the combinations formula together with the multiplication principle. 13 choices for the rank where the 3 cards come from, 12 choices for the rank where the 2 cards come from. Combinations of 4 choose 3 counts the number of ways to pick the 3 cards from the one rank. This counts the number of ways to pick the 2 cards from the other rank. Multiply that all out, and you come out with 3,744 as the total number of possible poker hands which give you a full house. Here's a typical full house. This would be a full house consisting of 3 kings and 2 sevens. The kings are one of the 13 ranks in the deck. King is one of the 13 ranks. So there are 13 possibilities for the rank from which the 3 cards should be chosen. In this instance, that rank is kings. The sevens are one of the remaining 12 ranks. One of the remaining ranks would be the rank where the 2 cards come from. 12 possibilities for that. The 3 kings shown are 3 of the 4 kings. So this counts the number of possibilities for which 3 of the 4 kings we would have. This counts the number of possibilities for which 2 of the 4 sevens we would have. And we're just looking at the same multiplication again with our eye on this concrete example. How many different ways could you form a committee of 3 from a group of 8 people? And secondly, if Jane is one of the 8 people, how many different ways could you form a committee with Jane as one of the committee members? First, how many ways to form a committee of 3 from a group of 8? This is a straightforward combination situation. We have 8 people to choose from. We're going to select 3 of them to be on our committee. Combinations formula, 8, choose 3. Choose 3 from the 8. The combinations formula gives you 56 ways of doing that. So there would be 56 possible committees if we had no restrictions on how we were making up the committee, if we could use any 3 people from the 8. In the second version of the question, we want to form the committee so that Jane is a member of the committee. If Jane is going to be one of the people on the committee, that means we're going to have only 2 other committee members besides Jane, and those 2 other committee members will have to be chosen from the other 7 people available, excluding Jane. So our problem boils down to choosing which 2 of the other 7 people besides Jane will serve on the committee in addition to Jane. Combinations of 7 choosing 2 is 21. So there are 21 ways to choose the additional committee members in addition to Jane to fill out the 3-member committee. So that gives us 21 ways of constituting a 3-member committee with Jane as a member. You might want to think of this, if you want to really think in terms of the full committee, you might think of forming the committee by picking Jane as one of the people. So first we're picking one person from the one person who is Jane, and then we're picking 2 of the other 7 people to get our total of 3 people for the committee. So if you think of these 2 sequential steps, we're picking Jane from Jane, only one way of doing that, times we're picking 2 of the other 7, and that will give us a 3-member committee with Jane as one of the members. But in any case, however you think about it, 21 ways to do it. If we're including Jane on the committee, 56 possible committees if we have no restriction on which 3 people we choose. 3 boys and 4 girls have bought tickets for a row of 7 seats at a movie. And how many ways can they arrange themselves in the seats? I've drawn a picture here. Think of these 7 blanks as being the 7 seats. And we want to distribute 3 boys and 4 girls in those 7 seats. And the question is, in how many ways can they arrange themselves? The answer is 7 factorial. This is a pure permutations question. You have 7 people altogether, 3 boys and 4 girls make 7 people. If you simply ask the question, how many possible arrangements are there for those 7 people occupying those 7 seats, that logically is equivalent to simply asking how many ways can you take those 7 people and arrange them in a row in those 7 seats. That's a pure permutation situation. The number of permutations, the number of ordered arrangements of 7 objects is 7 factorial, 5040. Now let's change the rules a bit and ask how many ways of doing it if the boys are all going to sit together and the girls are all going to sit together. One way you might start to think about this situation is to say, well, if the boys are going to sit together and the girls are going to sit together, then we either have to put the boys on the left end and the girls on the right end, or vice versa, girls on the left and boys on the right. If we're going to put the boys on the left and the girls on the right, since we have 3 boys and 4 girls, that means we'll have boys in these 3 spots, girls in these 4 spots. And if we're doing it that way, we can arrange the boys in their 3 seats, since we have 3 boys to be arranged in these 3 seats. That's counting the number of ways to put the boys in those 3 seats is just counting the permutations of 3 objects, so that would be 3 factorial. You can arrange the girls in these 4 seats in 4 factorial ways, 4 choices for which girl goes here, times 3, times 2, times 1. So I count the number of ways to putting the boys in their 3 seats, count the number of ways of putting the girls in their 4 seats, and then why do I multiply? It's just the multiplication principle, isn't it? If I'm going to count the number of ways of doing this kind of arrangement, I can do it by counting the number of ways to place the boys here, counting the number of ways to place the girls here, and then multiplying those 2 numbers. I get 144. So there's 144 ways to arrange the 7 kids so they look like this. Boys on the left, girls on the right. But that's not the answer to the question, is it? Because the question doesn't say the boys have to be on the left and the girls on the right. I also have the possibility of putting the boys on the right and the girls on the left. And if I did it that way, I would count an additional 144 ways of doing it just like that. It would be a very similar problem involving the same numbers. So I had 144 ways of doing it with the boys on the left and the girls on the right. I would get another 144 ways of doing it with the girls on the left and the boys on the right, put all that together, and I would have 288 ways of arranging them with the boys sitting together and the girls sitting together. Now let's change the rules a bit. Same group of people, 3 boys and 4 girls. Now we want to arrange them so that no one sits beside a person of the same sex. No one sits beside a person of the same sex that they are. If you think about it, that means we have to put them down in the pattern shown here. Since we have 4 girls and 3 boys, if we're going to alternate the sexes, we have to put the girls on the ends because we have to put girls on the ends because we have 1 more girl than we do boys. So we have to go girl, boy, girl, boy, girl, boy, girl. No choice about it. How can we count the number of arrangements that we do that? Well, you have a variety of ways you can do it. You can think pretty much like we did before. If you know the boys have to occupy these 3 spots, that gives you 3 choices for which boy goes here, times 2 for which one goes here, times 1 for which one goes here. So even though the spots are not side by side, it's still 3 factorial ways of putting the boys in their 3 spots and 4 factorial ways of putting the 4 girls in their 4 spots. So we still get 144 ways of doing it. Now there's no doubling involved. This is the final answer because this is the only way to do it, which this is the only pattern we can follow which meets the requirement of alternating the sexes.